Greetings, YouTube. Beautiful mind here. So we have completed chapter 1 on differentiation. So that was kind of like an introduction to differentiation. And now we're going to be moving into chapter 2. Chapter 2 is going to be focused on exponential and log functions, right? So with section 2.1, we have exponential and log functions of natural base E. And a couple of objectives here. We like to graph and solve exponential functions of the natural base E, and we like to graph and solve log functions of the natural base E, okay? So definition, the natural base E, denoted as E, is the value given by the limit as n goes to infinity of this expression, and it's equal to this, all right? You know, I don't think we're going to be using this limit definition like that. The main thing you need to know is that E is just a function, and it's equal. It's similar to like pi. It's similar like pi. You know how like pi is 3.14. So E in this context is going to be this guy here. Okay. And we have continuous exponential growth. A quantity P growing continuously at annual percentage rate R expressed as a decimal has a future value after t years given by this. So this is like from continuous compound interest. I call this like PERT. So whenever I'm doing continuous compound interest, I would do A equals PERT P e to the RT. But you can apply it to like things outside of continuous compound interest. Like so let's just see some examples. So with example 1, we have this one on continuous growth. Lewis invests, is that Lewis or Louise? Anyway, Lewis invests $5,000 in an account that earns an annual interest rate of 3.25%. Find the future value of Lewis's account after 5 years if the interest is compounded continuously. So now again, when we're using continuous compound interest, A equals P e to the RT, okay? And the future value, so we want to find A after 5 years when the principal is $5,000. So we're going to use E, the rate, 3.25%. So with this formula, the rate has to be converted to a decimal. Right now it's a percent form. So you can kind of look at this percent symbol as like per 100 or 1 over 100. So if you divide this by 100, it moves the decimal to the left 2 places. Right? So then 3.25% as a decimal is going to be 0.325, right? And we said the time is 5 years. Let my trusted dusty rusty. Save file. Now it keeps making me reload it each time. So I don't know. Time. Okay. And let's change this view to a single page. Okay. This in the calculator. So I'm just going to say 5,000 times E to 0.325 times 5. To the nearest cent, 24 cents, right? 58.82. 58.82 and 24. $182.24. $82.24, 58.82.24. Okay. As of late, let's move you over here. Even the quick checks is exercises for you since we just have so much information that we're going through. If you'd like to see like me go through these, just let me know, and I'm a dedicated YouTube videos walking us through any of these quick checks. So then we have another definition. For any positive number x, the natural log or log base e of x is given by this. So the natural log of x is just going to be the log base e of x. The equation y equals natural log is equivalent to, so now, I think like in the past, college algebra, this is a topic that we actually used to go through in just college algebra, but it was different at that time. So I guess the institution felt that we were putting too much information in college algebra, so they broke college algebra up into 2 courses. So with this, for instance, let me kind of do this the following. So y equals the natural log of x. We said, like in the line above, that natural log of x is log base e of x. So this is going to be y equals log base e of x, right? So then whenever we want to write logs as exponents, we basically swing the base, right? So if that base e swings over and becomes the base of our exponent, now we're going to have e to the power of y equals x. And you can see it here. We can write all exponentials as logs. Basically, if you just swing the base, right? That comes out of the discussion of inverses. Okay. We're asked to find each of the following. If necessary, use a calculator to approximate the value, to approximate values to 3 decimal places, right? Let's see. Okay, I kind of want to do this one like this, right? So we could set it equal to y, and let me go back to the line. Y, right? So then what we really have, we have log base e of e to the power 4 equals y, right? So then you can swing the base and rewrite this log as an exponential. So this is going to be the same as, and I'm just going to kind of continue over to the side. This is to the 4 equals e to the y. So then for these 2 exponentials to be equal, y has to equal 4. Okay, that's one way of going about it. With the next one. One log base e of 1 equals x. But then if we swing the base and rewrite this log as an exponential, this is going to be the same as 1 equals e to the power of x. So then this is 1. 1 is the same as e to the power of 0. Right? So then x equals 0. Natural log of 1 equals x. All right, let me be consistent. There. Let me get rid of this. Natural log of 1 is 0. Okay. I'm going to kind of start using some of the properties now instead of writing it in this expanded form. So natural log and e are inverses of each other. They essentially cancel each other out, all right? So then this -1, it can actually just come down. So because the natural log and e cancel each other, this is just going to be -1. We can explain it in a similar fashion that we did for parts A and B, but a lot of these examples are like properties and they go a lot faster. Let me think about this one. So this one I'm going to use the original technique. I'm going to set it equal to some y, right? So then this is going to be the same as log base e of 20 equals y. Now, if we were to rewrite this as an exponential, e equals e to the power of y. Actually, we should just use a calculator off the rip. I'm going to scrap all of that and just use my calculator. All right, I'm just going to make a note and just say, hey, just use the calculator. feel like you can type that in the calculator, so I'm not going to do it. -0, -1, and then whatever the calculator says. It's 4, 0, -1, and then using the calculator, we get approximately 2.996, right? I actually kind of use some of these properties. I just went on to started using them. So, okay, the log of a product is going to be the same as the sum of the logs, right? So if we have the log of something times something else, we can rewrite that as the log of the first thing plus the log of the second. The log of the quotient is going to be the difference of the logs, right? Or this is one that you saw me use already. The log of the power is going to be the power times the log. Natural log and e cancel each other, so that's 1 there. Notice that there's also an implied 1 on the e. So if you use property 3, the 1 can come down, natural log and e cancel. You know, properties 1, 2, and 3 require that m and n are positive. Okay. The natural log of 1 is 0. It's called change of base formula, right? Where you have the log base b of m. This is the same as the log of m divided by the log of b. The log of m divided by the log of b. That's the change of base formula. Some work. I feel like something's a little off there. Let me think about it for a moment. Log of m is going to be log of m base e. Log of m over the log of e. It should be an e, or this has to be changed. I feel like this should be log base b over here. Yeah. Log base b here. But this looks a little off. That's a suspect. Okay. Natural log of e, again, the x can come down. Natural log of e is 1. So then they cancel, right? And then also because e and natural logs are inverse of each other, they cancel, and that leaves us with the x. I feel like these, you kind of get used to these properties the more examples that you work, right? They kind of just start to come out. So in this example, we're given that the natural log of 2 is going to be this, and the natural log of 3 is this. Using the properties of natural logs, or use the properties of natural logs to find each of the following, right? Okay. So for the log of 6, log of 6 is the same as the natural log of 2 times 3, right? But we just said that the log of a product is the same as the sum of the logs. So this is the same as the natural log of 2 plus the natural log of 3. So then that's going to be 0.6931 plus 1.0986. We get those together. That's 1.0986. Is what? 9 times 9? So as the log of the log of 3 to the power of 4. Well, this is going to be 4, but we already said the natural log of 3. So it's 4 times the natural log of 3. So this gives us 1.0986. $32, 4 carried to 3, 36, 9 carried to 3. It's 4 times 1.0986.
4.0986 is 4.3944.
Okay. All right, so I think we said another property was that the log of the quotient becomes the difference of the logs. So this is going to be the same as the natural log of 1 minus the natural log of 3. We said the log of 1 is what, 0? So this term goes to 0. And natural log of 3 they gave us. So this is going to be negative 1.0986. First we can use the product rule. The log of the product becomes the sum of the logs. So this is going to be the natural log of 2. The natural log of e to the power 5. Natural log of 2 is given to us, 0.6931. Natural log of e to the 5, use the power rule, and natural log and e cancel each other out so that it becomes just 5. So then ultimately this is going to be 5.6931. So then log of 3 base 2, we can use the change of base formula. We can rewrite this as natural log of 3 over natural log of 2. 1.0, that's not 0. 86 divided by 0.6931. Hey Siri, what's 1.0986 divided by 0.6931?
1.0986 divided by 0.693. Is about 1.585.
Should know approximate, but I'm just going to go with it for now. $79, 17, 39, 44, 986, 5.1. Okay. Got a negative? Yeah, we got a negative. 69, 31, and 585. Like, right. It said approximately. So anyway, that's fine. Okay. Now we have this theorem that says that the natural log of x exists only for positive number x. So the domain of the log function is 0 to infinity. The natural log of x is negative or below the x-axis for any x between 0 and 1. Natural log of x equals 0 when x is 1, and the natural log of x is positive or above the x-axis when x is strictly greater than 1. The function f of x equals natural log of x is always increasing, and the range is always, right? So we'll see the graph. We'll see the graph of the natural log momentarily. Generally speaking, the graph of the log function, say this is like 1, the vertical asymptote of the y-axis, and basically comes up like this, passes through that point, and then goes up like this. This is the general shape of the log function. The domain of this. So again, when we take log, we can only I forgot what that was called. here, this guy has to be strictly greater than 0. We can't take the log of negative numbers, nor can we take the log of 0. So this part has to be strictly greater than 0. So then we say 5 minus 2x has to be strictly greater than 0. So then if we solve this, add and divide, we get 5 by 2 is strictly greater than x. We're talking about from negative infinity up to 5 halves. And I think both of these get parentheses. I've been leaving them as exercises for you just for the sake of time. And in this example, we're actually solve the following exponential equation using logarithms and to give answers to 3 decimal places. So for part A, we're starting with e to the power of 3x equals 2, right? Let's see. We can take the log on both sides, right? So we can do the natural log of this, natural log of this. On the left, these guys are going to cancel, and it's going to bring that 3x out of the exponent. So we're going to have 3x on the left. On the right, we're going to have natural log of 2. So then if we divide both sides by 3, x equals the natural log of 2 over 3. And then for the rest of it, we'll use a calculator. Log of 2 divided by 3. Is 231 approximately. E to the 0.015 t equals 750. Okay. Both sides by 250, 0.015 t. And it doesn't hurt with these to pause like at the start and try it yourself, see how far you can take it. And then unpause it and see how did you do in comparison. But 25 was what, 3? So then to get that out of the exponent, we take the log on both sides. Natural log and e cancel, and this comes out of the exponent. So then we'll have 0.015 t equals the natural log of 3. Ultimately, t is going to be the natural log of 3 over 0.015. Divided